Hi there, this is Math 8, Unit 5, Lesson 6. Today is even more graphs of functions. So here we go, we're going to be drawing some graphs from stories today, and so we're going to have some pictures that tell a story, and then we're going to kind of go through and show how that would look in graph form. So we began first of all with 5 pictures of a dog taken at equal intervals of time. And so, granted, this is like a little black and white version of it. If I put my iPad up, and it's a little bit better in color, maybe not too much with the glare of my camera, but anyways, you have that in your book. And so you had a picture of a dog who's just chilling and hanging out here on the edge of the grass. So there's our dog right there. He's still sitting there right there, hasn't started to move. Then we see that the dog starts to pop up and come towards the camera. It's getting closer, and then finally he's almost to you, right? So there's 5 pictures of this dog. Now it says that Diego and Lynn drew different graphs to represent the situation. So they both saw the situation, and they made 2 different graphs to explain what they saw happening. Now they both used time as the independent variable. So time is down here on the x-axis, right? That's where time's going to be. And what do you think each one used for the dependent variable? Explain your reasoning. So this is where you had to think about, what did they decide to make the y value of? What was the y value? Well, for Diego, we'll take a look at it, and again, it's all based upon the picture right here. For Diego, we see that the dog is definitely staying still for those first couple intervals, which is what we see here. That's that straight line piece, right? It's a straight line, it's not moving. There's the dog hanging out for 2 pictures. Lynn does the same exact thing, except she starts it way up here. So in Diego's and Lynn's, they have the same sitting still time, except one seems to be down here at what you might call, like, maybe this is a value of 1, and maybe we said this is like 10. I'm just making up numbers. That doesn't really mean what it is. But in terms of this is 0, I know that. So if that's 1, I can make that 1. Let's put that to 10. So 1 is starting at 1, and Lynn is starting at 10. So that starting point is a big deal. And we can see with Diego's, it gets from 1 and it gets goes up to 10, right? See how it matches right there? It gets up to 10 at the end. Whereas for Lynn's, it starts at 10 and then ends down here at 1, right? So it's like it's traveling a different amount or a different distance. Hard to say what's going on, but let's see. In the picture, you have to decide what your perspective is going to be. Is the dog getting closer to you? Let's say you're the person here with the camera taking a picture, right? And so you have your camera here and you're taking a picture of the dog, right? So is the dog getting closer to the camera as the graph goes on? That's one way of thinking about it, right? Or we could also take a look at how far it is from maybe it over here, it has its bowl of food. And we can't see the bowl of food, but as time goes on, and as the dog moves, it's moving further away from the food. Depends on how you want to look at that, right? So, for example, in Diego's graph, okay, we could say that the dog is moving away from the food, okay? So the food is down here at 1, moving away from the food and getting closer to the point 10, which is where the camera is at, over here. In Lynn's graph, we could say this is the distance it starts away from the camera. It's 10 meters or 10 whatever feet away from the camera, and then as the dog comes closer, it gets closer to the camera. So it depends on what you want to say. This could be a graph showing the distance again from the food, if I put a bowl of food right there, or really what you see in your picture is the edge of the lawn, right? Because there's the edge right there. So the distance from the edge is growing as he moves further away. And this graph could be showing the distance from the camera, right? It starts 10 meters or 10 feet away, and at the end it gets to be very close to the camera as the dog approaches and comes nearer. Okay, so that's just kind of some ideas. Again, there's no right or wrong there totally. It's just you have to be able to explain, and that's part of what today's lesson is about, is you explaining what do you see happening and what do you think. Let's look at the next page. For each situation, it says, name the independent and dependent variables, pick the graph that best fits the situation, or graph one if one's not provided, label the axes, and then decide which quantity is a function of which, and explain. And so here we go. It says Jada is training for a swimming race. The more she practices, the less time it takes for her to swim 1 lap. Okay, so when she practices, this is what she's going to do. She has to decide that. That's the independent variable. The more she practices, the less time it takes is going to become less. So our independent variable is going to be the time practice. Our dependent variable becomes the time it takes to swim 1 lap. So what we should see is that her time to swim should be decreasing as she practices more. So the more she practices, the less time it takes to swim 1 lap. So down below, we're going to make time practicing our independent variable down below, our x. So this is our time practicing. Okay, that's our practice time. So if this is time practicing, what's happening with each of the graph? If that's the time practicing, and this becomes our time to swim 1 lap all the way throughout, is the time to swim 1 lap decreasing as she practices more? In this case, the time is indeed decreasing as she practices more. Over here, we can see the more she practices, the longer it takes, right? That's an increase to swim 1 lap. Here, in this great graph here, you have her starting, and it tends to be that the more she practices, the longer it takes, and then she just kind of stops. It doesn't get any better. She kind of flatlines there. Okay? So the one that seems to make the most sense would be this graph right here, showing that the time practicing is going to lead to a decrease in the amount of time to swim 1 lap. So this is our independent variable here, and our dependent variable there. All right? So which is a function of what? We would say here that the time to swim 1 lap is a function of the amount of practice. Amount of practice time. Okay? So how fast you can swim 1 lap depends on how much you practice. And that's what we would say there in terms of it being a function like that. Number 2, it says Andre adds some money to a jar in his room each week for 3 weeks and then takes out some in week 4. So for 3 weeks he adds, and then he takes something out. Okay? We don't know how much that is. It's just some money is what he's adding there. That's what it's going to be. So for our independent variable, we're going to say that weeks is our independent variable. Okay? So each week he's adding something here. All right, we have 4 weeks there. Now, what's dependent is going to be the amount of money. Okay? That's the dependent part. Now, what's weird in this one here is we know on like week 1, he adds some money, and he has whatever that's going to be. On week 2, he adds some more money, and it puts him up to this amount there. Week 3, he adds some more money. And on week 4, he takes some out. We have no idea how much he takes out, but he takes some out. So it looks something like this, right? He's adding, and taking some out like so. And so in this case, well, we'd say our independent value is the weeks, our dependent value is the money that he has. That's what that graph would look like, so to speak. And so as a function, we would say that the amount of money in his jar is a function of the week. Meaning, how much money he has depends on how the week went. Okay? So if it was a week where he made money, he has money in the jar. If it was a week where he had to spend money, he has less money in the jar. And that's all we can really say about that one. Just interesting. All right, let's take a look at the next one. 6.3, it's a little story. This is called Sketching a Story About a Boy and a Bike. Okay, and so you're going to have a tool, it says, from your teacher to create a visual display with your group. Create a display that shows your response to each question. And so the idea here is that you're going to read a story here, and you're going to create a set of axes, right, like this. You're going to graph the story, whatever that might be, You're going to label this with what is our x value and our y value, or our independent and our dependent value there. Okay, describe which is a quantity, what quantity is a function of which one, and then based on your graph, is his friend's house or park closer to Noah's home? Answer some questions about which one's closer to what, and then read your story and see if it makes sense. So here's our story. Noah was at home. He got on his bike. That's our starting point. He got on his bike and rode to his friend's house, point number one, where he's going there, and stayed there for a while. So he stayed there for a while. Then he rode home again. Then he rode to the park. Then he rode home again. All right, so that's kind of our story here of what's taking place in this situation. There's a couple ways to graph this one, so I'm going to show you one way, and hopefully you do this in your class with your teammates as well, your partners. So you get to decide how you want to set it up. That's what's kind of cool, and you just have to be able to explain it. So here's one way of looking at it. Okay, we could say something like this. We can make a little graph like so, and we could mark out the time here, and we could say distance traveled. All right, maybe I do distance traveled. Maybe that's what I'm doing there. I don't know. Right? Let's assume I don't know what all these things are about, and I just do distance traveled. That's one way of looking at it. So we know that Noah was at home, and he starts at home, or distance traveled, I should say, yeah, total. So we start at the starting point, wherever we're going to be. He gets on his bike and goes to a friend's house, so we know he's going to ride some distance to a friend's house, whatever that's going to be. No values, just that's where it's going to be. Then it says he stays there for a while, so we could have him just hanging out. He's not traveling, he's parked his bike and he's hanging out there. Then he rides home again. Now this is where your graph could be different. If I'm just measuring the distance traveled, if he's just going home, then that's just more distance traveled over time. It should be the same amount as that, and so I just know he went home. That's all I know. Now what's weird about the story is it says, then he went home, then he rode to the park, then he rode home again. I don't know if he paused here and stopped in between those things. Did he just like drive to his house and like touch the door and then turn around and run back to the park? I don't know. Let's pretend at least that he stopped for a second at home. Maybe he got a drink of water. I don't know. Right? That's a question mark there. And then he goes to the park. Okay. I'm guessing he goes to the park, and maybe he just went to the park and drove to the park and then turned right back around and went back home. Oops, not going down. Sorry. Oops, don't do that. And then he goes right back home. And so we just draw the distance back home. And now he's back home. So this is to the house. This is to the friend's house F. This is the, that's the part there. This is back to home. This is the park, and this is back to home. So one graph could look something like this, where I'm just demonstrating the distance that he's traveled. He started here at going maybe 0 miles, and these are all maybe mile marks. So by the end of the day, he's gone 4 miles on his bike. Just making that up, right? So that's what I might say there. Time becomes my independent variable, right? Because that's something that's just going on. But the distance traveled depends on the amount of time that he spent driving his bike. So that becomes our dependent variable there. In our case, in this case here, we said distance traveled is a function of time, because how far he travels depends upon how much time he's been doing his little trips back and forth. All right, so that's one way of looking at this graph here. It does ask in question 4, based upon the graph that you made up, is the friend's house or the park closer to his home? To figure that out, what you want to do is you'd have to look at your graph and decide, well, which one had the greater distance, right? So here, to go from my friend's house to the home was that far, whatever distance that happens to be. And then here we said to go from home to the park was that distance, which looks like about a little bit shorter amount of space there. So based upon my graph, just again, this is what I just drew, the friend's house was further away than the park. Is that right, wrong? It's up to you. You just have to be able to explain that. Another way of graphing this could look something like this, and I did this one in, oops, that's kind of crazy. Don't want to open the App Store. Where did it go? That's kind of funny. Let's see here. That's odd. Nope. How do you like that? Sorry guys, I just had it open and moved the iPad and away. Oh, now it's back. Okay, so if you use the computer version of this, right, you can create your own graph in the little what do you call this thing, on the little thing on the computer. Here's my iPad. So what I did in this one is I made a totally different kind of graph, right? I said this graph here, I still have time as the bottom, but here I'm on my y-axis, I'm using the distance from home. Okay, so right here on A, he is at home, and then B, he goes to his friend's house. So he's gone whatever 5 miles maybe from home, probably pretty far. So he goes away from the home, hangs out at his friend's house, and drives back home here. Hangs out at home, and then he goes to the park. So this is again our distance from home. So he's going away from home, hanging out at the park, and then going back to home. So this is a different graph altogether, but it's really telling the same story, but I'm changing the value or the label of what's in the dependent axis there as turning into the distance from home. So as he goes away from home, the distance increases. As he comes back to home, the distance will decrease there. So similar story, or sorry, same story, just a different graph, a different way of illustrating that story. Okay, I just want to show that there as a different way. So that's one way. The one I did on the computer is another way. They all work. Okay, and so that's what we're doing today. Today's whole thing is just looking at a graph and being able to tell a story about that graph, or using information about what's happening there, knowing that you have independent and dependent variables along the way. All right, so let's take a moment to do our homework, and we'll pause there, and we'll check our homework together. Okay, so here's your homework. It says match the graph to the following situations. You can use the graph multiple times. For each match, now name the possible independent and dependent variables and how you'd label the axes. Okay, so the first one says, Tyler pours the same amount of milk from a bottle every morning. So he has a bottle of milk, all right, and he's pouring milk from it every morning. So we're decreasing the amount of milk every morning as we pour the same amount every time. So we should see something decreasing. I notice that A is not a decreasing kind of graph, it's increasing, so that's not going to quite work. B shows me a constant decrease, and I notice that the decrease seems to be the same amount each time, right, in little intervals like that. C, it is decreasing, but it's not decreasing at the same amount every single time. So the one that makes the most sense for this one would be B. B seems to work the best with this one here, where this could be the days, right? Each day, maybe that's days, hard to say. And then, yeah, maybe that's days. And then over here, this could be the amount of milk. Maybe you have the amount of milk left, perhaps, because it starts with some and then it decreases as it goes along. Each day decreases. That could work. Just an idea, but that's what we have there. B is a plant grows the same amount every week. So it's growing, so we should see some growth, right? And it's the same amount, so it should be a constant amount, like a linear amount, not like whoop, or just something shoots up. So these are declining. A is the only one that shows an increase, and it's a constant line, so we would say A goes there. Okay, so this could be the number of weeks over here, and this would be the height of a tree, or height of the plant there, showing a constant growth. And that becomes our independent, and that's our dependent. For C, we have a day started very warm, but then it got colder. So we're going to start up warm, and then we're going to decrease in our temperature as it gets colder. Okay, so this could be a good one for C, where this is time, and up here on our dependent value, that's our temperature. So it starts high and then drops down and decreases. That would make good sense for C. So I put this as C, and this one, yeah, that's what I got. So C goes to C. And the last one here, D, a carnival has an entry fee of $5 and tickets for rides cost $1 each. So this is a good one because it has a starting point where you start at 5, right? Let's say this is 5. You don't start at the origin, and then every time you do a ride, it's going to cost another $1, another $1, another $1. Okay? And so this is going to be the, in this case here, we would say this is going to be your cost, right? And this is going to be your number of tickets. So the number of tickets you have is going to determine your cost. So tickets becomes the independent variable and cost becomes your dependent. The cost depends on how many tickets you end up buying. So could that be with another graph? Sure. It could also be with this one where you're starting at 5 and then increasing as you go along, but the labels would be a little different. All right, number 2 says Jada fills her aquarium with water. The graph shows the height of the water in centimeters in the aquarium as a function of time in minutes. Invent a story of how Jada fills the aquarium that fits the graph. So this is one where you just need to look and see what's happening in this story, in this graph, and tell a story about it. We can see with time being down here, right, and the height of the water in the aquarium that she's definitely filling it up. There's a moment where nothing's happening. It's being filled up again, and then it's starting to decrease a little bit, and then it stays the same. So your job is to tell a story about what's happening in each of these places. Your story should talk about that place, this place, and the drop, and there. So you should actually have 1, 2, 3, 4, 5 parts to your story. All right, and I'm not going to write one there. That's for you to be creative about and make up a story of what's happening with the height of water, the amounts of water in the aquarium over time. Okay, so I'm going to move to the next section. Okay, recall the formula for area of a circle. Write an equation relating circle's radius and area A. So for the formula for area of a circle is area equals pi r squared. It's radius squared times pi determines our area there. Question B says, is area a function of the radius? Is radius a function of area? And what we would say is yes for both. Okay, the area is determined by the radius, right? It depends on the radius. The radius can be the independent factor here, and whatever value I put in that will give me an outcome of an area there. Now the reason we say yes for both is we can rewrite this equation, and we could say, well, let's rewrite it. Area equals pi r squared. If we could get r by itself, then it's going to work. So let's say here we divide both sides by pi. So you have a over pi equals r squared. To get the r by itself, we do square root. Now this is more than you need to do, right? But if I took the square root of the area over pi, that would be equal to r. And in this case, r becomes a function, the radius becomes a function of a. Because a radius has to be positive, it can work this way. If the radius could be a negative value, it wouldn't work. But because radius is positive, yes, radius can be a function of area. We just probably wouldn't ever set it up that way, okay? Okay, fill in the missing parts of the table. Again, using our formula, area equals pi r squared. So if r is 3, what is 3 squared? 3 squared is 9, so we would just say 9 pi. Okay, over here we have 1/2 squared. Well, 1/2 times 1/2 is 1/4, so we would just say this is going to be 1/4 pi. On the area side, to go back the other way, they're already giving us a number, 16 and 100, and instead of squaring it, we have to go the other way, take the square root of that, or think about what two numbers multiply together to get you to 16. That's going to be 4. 4 times 4 is 16, and there's our pi from our formula. And then over here, what two numbers multiply together to get you 100? That's going to be 10. All right, and finally number 4, it says the points with coordinates 4, 8, 2, 10, 5, 7 all lie on the line 2x plus 2y equals 24. Create a graph, plot the points, and sketch the line. And then what is the slope of the line you graphed? We're looking for the slope. And what's it tell you about the relationship between the lengths and widths of rectangles with perimeter of 24? So this is actually the formula to find a length and width of a rectangle with a perimeter 24, right? It's 2x plus 2y, like your 2 times the length plus 2 times the width is going to give you your perimeter of a rectangle. So let's use these points here, 4, 8, 2, 10, 5, 7, and plot them out. On the next page over here, we do have a piece of graph paper to help us do this. And so again, I'm going to just jot our points down here just so I can see what they are. We had 4, 8. we had 2 comma 10, and we're given 5 comma 7 that are all on this line. Okay, and so if we're going to sketch this out, all right, I can draw a line here. That's my y. Here's my x, like that. And then we can say this is a value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5, 6. Okay? And so we have 0.4 comma 8, which is going to be here. We have 2 comma 10, which is here. And we have 5 comma 7, which is here. So that's what our points look like when we draw them out like such. And then if we were to draw our line and connect our dots, our line looks like this, right? And that's what we have there for our graph. So knowing that to be true, okay, we've created it, plot the points, sketch the line. What's the slope of the line you graphed? Well, the slope is going to be, there's two ways of looking at it. Slope is your rise, how much it goes up or down over your run. And we're looking here from point to point. Let's look here. We're going down 1 over 1. So we're going to be going down 1 over 1. So our slope is going to be simply a -1. The other way you could solve this, which we've done before in previous lessons, right, is we take a look at the points themselves. And we say, well, let's use the values of those points. So here we have 4 comma 8, and here we have 5 comma 7. And the way we find the slope, if you recall, using the points, is we do y2 minus y1 over x2 minus x1, and we plug in those values. So this is our, let's say this is our second value, 2. This becomes our, so we'll make this our number 1, and this one number 2, okay? So our y2 here is 7, minus the y1, which is 8, over x2, which is 5, minus the x1, which is 4. So 7 minus 8 is -1, 5 minus 4 is 1, we're looking the same, and so our slope is -1. So that's how we solve for slope, in case you were kind of forgetting how that worked there. I could use the other points too, and it would work the same. I would just end up with 2 over -2 or -2 over 2. It works out just fine. Okay, so that's our slope there. The next question was, what does the slope tell you about the relationship between lengths and widths of rectangles with a perimeter of 24? So what it's telling me here is this, is that every time I add, let's put a point here just to show you, 3 comma 9, and this is 2 comma 10. Every time I add a length, or add to the width, I have to decrease the length. So let's think here. If this number goes up 1, 2 to 3, what's happening in the y? It's decreasing by 1. If this goes up, that goes down, up, down, up, down. So that's our pattern here. So when it comes to a rectangle, whenever I add another length to the width, I have to take one away from the length. If I add an x, I take away a y. If I add a y, I take away an x. So there's that give and take of back and forth, one-to-one relationship there. All right, that's it for today. We will see you next time.